move on to the last talk of the day, which is going to be about agentic workflows at ALCF. What I'm starting here is following the README file that is on the ALCF hands-on HPC workshop repository, and then under Agentic Workflows, there's some slides that are also on the GitHub that I'm going to transition to in a second to do the introduction, and then we'll move on to go over two examples, a multi-system or remote example, and we'll talk in a second about what that really means, and then finally a single system or a local example of a workflow. So I'll also start by transitioning to the slides and introducing myself. I'm Riccardo Balin, assistant computational scientist at ALCF in the Data Services and Workflows group. And the slides, especially, and all the work really was a collaboration between a lot of people at ALCF and CPS. And in this talk, I'll also be sharing some of the information and the slides with Tang Pham, who is a postdoc in the computational science division at Argonne. So maybe start from the very beginning at a high level. What are agentic workflows? So perhaps an easy way to describe them is to say that they're AI-powered computational pipelines that can autonomously perform complex tasks. They can make decisions on the fly and adapt in real time based on intermediate results or even user input. They exhibit what we could say in quotes, agency or intelligence. Of course, this is in the context of things like LLMs, which means that they can do some reasoning, planning, or execution of tasks based on new results. And this is the idea is that this can be done with minimal human intervention. And so, again, this is intelligence in the sense that we can use large language models to interpret intermediate results, and then the model or the workflow itself will sort of plan what the next task is based on these AI models. So some key characteristics, perhaps, that we can highlight at the top level are the breakdown of complex tasks into discrete steps. This is really just a way of saying that we can compose agents where each agent is handling a specific sort of subtask to then combine all these agents together to then tackle more complex tasks that we as scientists would try to tackle. Again, there's this idea of autonomous or real-time decision making, the fact that the planning or even what steps to execute next isn't predetermined, but rather this can be determined autonomously by the workflow in real time based on intermediate results. And again, this goes into the adaptive execution.
Riccardo, could you
Yeah.
just share the screen of the GitHub rather than your whole laptop screen?
Sure. It's just that then I'll be transitioning to
Oh,
the
okay.
terminal
Then that's
for
fine.
the
That's fine.
this.
It was just for the recording purposes. Then that's fine.
Uh,
Sorry about that.
no problem. Thank you. But let me know if it's not very visible. I could try to make it bigger or
No, it looks good. It looks good.
okay. Thank you. So large language models, as many of us know, I think by now, can provide immense value to scientific research, but they can also struggle on complex topics due to maybe what's broadly called hallucination. So this is a very sort of straightforward example where the human provides a prompt to a large language model. In this case, the idea is to provide the smile string corresponding to the molecule that's then spelled out in words. And a large language model, in this case GPT-4o, would come back with the incorrect answer. And so how do we make generative AI or large language models more useful for science? And this is where agentic workflows, I think, really can come in and allow us to go beyond this sort of chatbot or question answer interaction that we would have with just simple large language models. And they can combine the power of generative AI with computational science tools that computational scientists have been using on HPC for many years. We can also combine research databases so that we can, through things like RAG, get more accurate data on or help the large language models get the information they need to answer our complex questions. And then, of course, in the context of agentic workflows at ALCF, they can leverage HPC resources that we provide. And so in this simple diagram here, you can see sort of the initial chatbot schematic goes from a prompt to the model, and then that just produces an output. But rather in an agentic workflow, the prompt is then spawning an interaction between one or multiple language models and then a set of tools that we can define in our workflow to then provide a more informative, more accurate output answer. So here then I'll let Teng take over and describe some of the work that they've been doing at LCF to build an agentic framework for computational chemistry.
Yes, thank you, Riccardo. Can you hear me well?
Yes.
Yes, so in this figure, we're showing a demonstration of ChemGraph, an agentic framework for computational chemistry workflow that we created. This framework aims to lower the entry barrier for researchers and students in chemistry and material science by abstracting a lot of technical hurdles, but still preserving the scientific rigor. In this figure, it's showing you that from a user prompt, the prompt is decomposed by a planar agent that split the user prompt, which can be a complex task, into multiple smaller subtasks. These subtasks will be sent to an executor agent that have access to a bunch of tools. These tools cover a broad range of computational chemistry, from cheminformatics to actually running molecular simulations using a wide range of methods, from semi-empirical ab initio method as well as the more recent machine learning into atomic potential. Once all the executor agent finish their two calls, the results are sent to an aggregator agent that return a final answer to the users based on the two calls. In the next slide, we are showing you an example where using this agentic framework, the large language model can overcome its problem with hallucination. On the left, you can see the previous slide that Riccardo showed, where large language model, even the good one like 4.0, it's giving you the wrong answer. On the right side, now using a much smaller model for mini, instead of trying to hallucinate or reason to get a smile string for the user, it actually invoke a tool call, giving the right parameters and give the user a correct answer. In a more complex example, in the next slide, in this one, ChemGraph is tasked with calculating reaction enthalpy for a given reaction, in this case, a methane combustion reaction. We asked ChemGraph to calculate this property using a specific computational method at a specific condition. The way that ChemGraph solved this problem is that the prompt from the user is first passed to a planar agent that decomposes into a smaller subtask. In this case, calculate this property for each of the molecule. Each of these subtasks is sent to executor agent that invoke different tool calls. And at the end, using the two output from each executor agent, an aggregator agent synthesizes a final answer based on the previous two call results. Could you go to the next slide, please? In this work, we also benchmark ChemGraph across different large language models for a wide range of tasks in computational chemistry. In the first plot on the left, you can see that we benchmark 4 different large language models, 3 proprietary models, which are 4.0 Mini, Cloud 3.5, and GPT-4. We also use the ALCF inference endpoint for the WAN 2.5 14 billion models. A quick summarize, what I'm showing you here is this is the benchmark for a system with single agent. And we show through our benchmark that small large language models are very effective for simple, well-defined tasks. However, as the task complexity or the number of tool calls increase, we saw a drop in performance. And that's where we introduced the multi-agent that I showed you earlier to reach higher accuracy, even with small large language models. The plot on the right-hand side is showing you the accuracy of the multi-agent system. And across the board, we show that by implementing a multi-agent system, the performance of the model increased significantly, and a lot of time with accuracy above 90%. ChemGraph also provide a chatbot interface where you can visualize things and results, the molecular structure, vibrational mode, and IR spectra for the molecule. All this evaluation will actually done both locally and on your CF supercomputer. ChemGraph is open source and available on GitHub, and we'll welcome any collaboration in early user. That's it for me, Riccardo.
Awesome. Thank you so much. Perhaps I'll stop here for a sec to see if there's any questions about ChemGraph. I can't see the chat, so please let me know if there's any in the chat. But if not, perhaps then we can move on. Thanks then for the overview of ChemGraph. This is actually part of the motivation why we wanted to talk about agentic workflows today. We've seen good success, but they're perhaps a bit of a new topic. And so what we've started to do at ALCF is to provide a repository. The link is provided here. We'll actually leverage that in a second for the hands-on examples, where we're starting to add at a high level patterns for some of these agentic workflows. In these examples, the science is fairly simplified, and the workflows are fairly simplified, but we're trying to really just demonstrate how you would set up your own workflow. And at the moment, we have two examples that I think cover a significant piece of the spectrum in terms of where we think users might want to entry this perhaps new field. The first one is multi-system or remote workflows, and that's actually building on a lot of what we've seen in the previous talks today with Globus Compute and the inference service. The idea is that the agents run and launch components on various ALCF or even local systems. So this is where the multi-system or remote idea comes in. For example, the LLMs are served remotely through the ALCF inference service, as we just saw. So why, some of the advantages of these multi-system remote workflows could be that there's perhaps a lower implementation complexity. That is, you can leverage, I think, a lot of these tools that we described today that make putting the pieces together a bit, in an easier fashion. You don't have to serve your own large language model on our compute nodes. You can use the inference service, and you can use global compute to launch jobs. It also means that you can target specific systems with each of the computational component of your workflow. So if things only need CPUs, you could use our CPU-only machine. If things need Aurora versus Polaris, you can target each of those individually. So this is perhaps a better way or a more efficient way to make use of your allocation on all of our different systems. And there's perhaps also better support for long-running workflows. That is, the agent themselves, the workflow can actually run on your local system, your laptop, and so it is maybe not interrupted, say by your SSH connection dropping, or if you're submitting jobs to our systems, even if our systems go under maintenance, your workflow can still run. It would just be waiting for that job to execute and come back with some results after the maintenance is complete. In terms of cons, perhaps the highest one is there's higher latency between tasks, right? The idea is that these tasks are running on different systems, and so you're subject to things like the scheduler or queues when you're running different jobs on, say, Aurora or Polaris. And also when querying the inference service, as we saw, it's very fast. However, if you need a certain model that is perhaps not being served at the moment, then there's a bit of overhead over there as well. The other type of workflow that we're going to be covering is the single system or local workflow. And in this case, the idea is that all agents are and all the components are running on the same system. And actually, even as we'll see in the example, within the same batch job, so directly on the compute node. So this means that you can still use the inference service if you want from the compute node, but it also means that you can serve your own large language model locally on the system nodes. And that's what the example will show. So advantages in this case, I would say, are lower latency between the tasks, right? You don't need to go through the scheduler, you need to wait sort of in the schedule in the queue once only for your batch job, but then all the components of the workflow don't need to go through the schedule anymore. And if you're serving your own LLM, then the latency in your inference request can be reduced over there as well. Another additional pro I would say is that I forgot to mention here is that you can serve your own large language model. So you can always go through the inference service and ask ALCF to serve a particular model that you're interested in. But if you're bringing your own to our system, then perhaps serving it yourself might also be an alternative approach. Disadvantages perhaps here are that there's maybe a bit of a higher implementation complexity. I would say that's specifically around serving the large language models or AI models in general. You are subject to queue limitations in this case. That is, your workflow cannot run, for days at a time, right? There are maximum runtimes or job limitation in terms of sizes once you're within this batch job framework. And then finally, that these local workflows may not use your allocation in the most efficient way. That is, say that you have some sequential steps in your workflow, and that's actually what we'll see in the examples where you're first doing, say, an inference request to a large language model and then decide, prepare some input parameters for a simulation. You're depending on how big your model is, you may be wasting some of the resources you need to run your simulation while this inference request is being done. And so the occupancy of the hardware, overall GPUs and CPUs of the entire location that you request to run this on may not be utilized particularly well, but you get sort of a faster throughput or lower latency in return. Maybe I can stop here for a sec to see if there's any questions at a high level what we're trying to cover today, the two examples. Okay. So then going back to the main README, what we'll see here is that there's links to specific examples that we've added to the repository I mentioned. And so I'll move on to a second to cover those. I did want to also mention that in the README, you'll see some specific notes on setting these examples up for the workflow. For example, using the right queue names for your Globus config, and then also, since maybe you're just starting, using things like debugging for verbosity and things like that. So I'll let you go through them. Just in the interest of time, I'll skip actually then to covering some of these examples. And first we'll start with this remote agent-driven simulation on Aurora. This is tutorial developed by Taylor Childers at Argonne. And I'll go through the README here. Actually, this is a tutorial file in that repository. Again, the links to these examples are all in the README, the main README for the workshop. So at a high level, there's really three components here. There's orchestration, and this is a LangGraph client. This is the actual workflow that's running with the different agents. We'll see that in a second. The second piece of this is AI inferencing, in this case, using the inference services on Sophia that were covered in the previous talk. And then through Globus Compute, again, a tool that was covered this afternoon, this allows us to submit jobs to, in this case, Polaris, since Aurora is down for maintenance. So Globus Compute is sort of the layer that really allows both the inferencing and the computation in this case to happen remotely relative to the client or to the workflow that's running. In terms of key technologies here, as we mentioned, LangGraph for the agentic workflow, Globus Compute, the inference service, and also OpenMM. In this case, it's the particular simulation that we're going to try to run, even though that I think is a bit less relevant. There's detailed information here on how to set everything up, since most of it relates to setting up Globus endpoints on your local machine or on one of our systems, and that was covered in the previous talk. I'll skip through that and actually just sort of go through covering the agent itself. So this is inside of source main.py. So I'll go over right there. And so here we're in remote Globus to Aurora src main.py. And so we'll see that we're again creating using LangGraph to create this agentic workflow. Really the things that we're also using are this Globus Compute wrapper from Globus Compute, and then also as you can see here, we are leveraging the inference service on Sophia with, in this case, this particular model. Perhaps what's important to define here, maybe to give an overview, is the idea that an agentic workflow is basically a series of agents that are passing around and updating, in this case, an agent state, which is really just a type of dictionary. So we initialize that here as a class at the top. And then what is interesting is then to go towards the bottom and then see how the workflow is defined. So in this create workflow function, you can see that that's where we're actually instantiating the workflow with state graph API and passing that state that we saw earlier. The next step would then be to create the nodes. The nodes are effectively the different computational points or the different tasks that are being executed. So you see that we first add a large language model analysis node. I'll show those in a second. We then go to a simulation node, and then finally a report node, which really just prints the output of the simulation in a nice readable format. So once we define the nodes, we then have to define edges. So this is how the different nodes are connected to each other, and so the progression of the workflow. The entry point in this case is the large language model analysis. That is, the workflow initiates by the user sending a prompt to a large language model for inference. That then spawns a simulation based on the results of that inference request. And then the simulation results then spawn the reporting of the output. And then finally that ends. So then we can compile the workflow at the bottom. Now, we try to keep this fairly easy so that to not overcomplicate things. And so we'll start by going over the actual nodes themselves, the agents. So again, this is using a lot of technology, as I mentioned, that we've already discussed. So perhaps I'll go through this a bit quickly. The first node that we talked about was that a large language model analysis. So as you can see here, it's taking the state as an input. And then what it's doing is it's trying to, using the OpenAPI API, configured for Sophia with the global authentication that's been already done sort of in the setup phase to pass this particular prompt. And this prompt is really just asking for some information on how should we set up an OpenMM simulation in terms of defining the time step, the temperature, and the number of steps for a particular protein. And that protein can be defined at runtime by the user. So you'll see that we invoke that LLM and get a response back. There's a bit of sort of trying to accept code here to make sure that we get the response in the format we need, just for this example, for simplicity. But the idea is to extract effectively these 4 pieces of information that then we pass to the next step, which is the simulation node. The simulation node, again, gets the agent state, which was updated with this information about the simulation that was provided by the large language model inference. We then go use Globus compute to submit the simulation. And again, we're passing the state here. The simulation, I won't have time to cover today, but it's a simple sort of OpenMM simulation that's just trying to run a simple compute the I think it's the binding energy of the enthalpy of a particular reaction with a protein, and there's a fallback in case there's any issues with that. But that's sort of the second step. And then finally, again, there's this report node that I mentioned, which is again taking the state, updated with the simulation results, and then is finally just printing the outputs of that simulation in a nice readable fashion. And we'll see that in a second. So if we go back to the main, we'll see that it's fairly straightforward in the sense that we parse some import arguments, we create that initial state that I mentioned, and then we create the workflow over here, and then we invoke the workflow. So the workflow is actually running within sort of this driver script, right? And so really what's using our ALCF systems is the inference service and then the simulation that we launch with Globus Compute. So if we go back to the README for this example, the tutorial, I'll skip over the setup again, because that's something that we've covered and just in the interest of time. I'll move over to actually how this is run. So effectively, once you have your Globus input started on, in this case, Polaris, and then authenticated, and in this case, I'm running the workflow on my laptop, you'll see that now we're ready to actually running the workflow. And so in terms of basic execution, you'll see sort of you need to clone the repository. There's information on how to activate a virtual environment. And then we're really just running this Python script. And this is, again, going to be run on my laptop. And we'll see how that is deployed, in this case on Polaris. So I moved over to my terminal. On the left, again, is my laptop in which I'm launching the workflow. In this case, I'm using the debug verbosity, so you'll see some extra outputs. But what is key here is that if we look at on the left, you should see that now there's this parcel global compute job. And this is the simulation that was submitted. So it's happening pretty fast. And so maybe once it's done, I'll go through and explain the different steps. But you see that it effectively, if we go back to the output, we'll see that it was able to start the workflow with this particular protein, running this particular model with this endpoint on Polaris. And so the first step, as we remember, was creating the large language model for our protein analysis. This is the particular prompt that was given. This was hard-coded in that main.py file. And then we see the large language model response right here. So it provided some information of what it thought the right time step, temperature, and number of steps were. Now, the next step would be to launch, in this case, it's not on Aurora, but it's on Polaris, but to launch the GPU simulation. So here we're using Globus Compute. And in terms of some of the drawbacks, as I mentioned earlier, this was submitted to the queue. Now, this was to the reservation, and so it went through the queue quite quickly. But you can see that you're still waiting for a number of seconds for that job to be submitted to the queue and then to eventually start. So that's sort of one of perhaps the drawbacks of these remote workflows. Here, there's a slight warning, as Christine mentioned, if your Python versions are slightly different between local and remote, you get this warning. In this case, the difference is only on the sort of third number here of the Python, so it wouldn't cause any issues, but you still get the warning. And so finally, we see that the simulation, or the job in this case, completed again quite quickly. Because these are really sort of easy simulations to run. And then the final report, as you can see here, is really just to print out some of that information in maybe a nice readable fashion. So I see that I'm running out of time a little bit, so I skip next to the local example. The local example is actually very similar in terms of what it's doing. The task that the workflow is executing. The only differences are really, as we mentioned in the introductory slides, that now we are submitting or executing the workflow within a batch job. So it's on a compute node of Polaris. And if you look at the instructions for running the demo, there's no actually use of Globus Compute, no authentication needed, but it actually starts with getting a compute node on Polaris in this case, and then starting the environment. So the next over here, so you'll see here I'm already on a compute node. And you see the first step is to actually start the VLLM server. So that's what I did here. That's one of the auxiliary scripts that we've provided in the example. We can actually tail that file to see the VLF server starting, and then once it's started, we can then execute the workflow. So this will take a second, and as it does, I'll go back to the README here. So we start the VLM server of a node. Again, this allows us to really serve whatever model we have decided to. In this case, for the workshop, I've made the weights of a particular model. In this case, it's the Llama 7B, one of the ones that is actually being provided in the inference service, but I made the weights available in the workshop directory so that you can serve it locally. So after we start the VLLM server, you can see that we can then call the driver, the main function of the workflow in a very similar way. And actually, I can open that real quick to show some of the main differences, which is really in how we are launching the large language model, how we're doing the LLM analysis, which is no longer using Sophia, but instead using this local host so that we are connecting to that VLLM server on the node that's listening for requests. Here there's a bit of a wrapper function just to wait for it to be ready in case you want to run the workflow right away before the VLLM server has spun up. You can see that the prompt that we're sending to the LLM is actually very similar. And then we're getting that response back. And then moving on to the next node of the workflow, that's the simulation. Again, you can see now in this case, we're actually just calling this runmd simulation function that's part of the simkernel.py script here, also in the source code, directly. There's no need to use Globus compute since we're already on the compute nodes. So going back to my terminal here on Polaris on the node, that interactive session I mentioned, we see from the log file of the VLLM server that the application was complete. So now the server is ready for us to submit requests to it. And so we can run that. Let me see. Yep. We can run the main script of the workflow, similarly to what we did in the remote case, but you'll see the output looks a bit differently. It also ran much more quickly. I don't know if you noticed that there was really effectively no latency in the inference request and effectively no latency also in the simulation as well. Sorry, I scrolled too far. We're seeing again, we're starting with this LLM query with the prompt. The LLM replied with its suggestions for how the simulation should be run. And then we moved over to, again, this is not Aurora, but Polaris, given the fact that it's under maintenance. But then we move on to the simulation step. And then finally, the report at the end. So I apologize, I went a minute over. There was a lot to cover and maybe not enough time. But I can stop here and take any questions, and also happy to follow up with anybody offline via Slack or email.